So far, we have seen the high temperature behavior for the heat capacity that is Dulong Petit law, that the heat capacity per mole, molar specific heat, saturates at 3 and 3R for high temperature limit. And in the Einstein model, we have taken into account quantization of energy in the harmonic oscillator, and we have considered only one mode with angular frequency omega. We looked at the average occupation of this mode, the number of phonons that are in this mode at a temperature T, and we have found that the specific heat should be dropping to zero at zero temperature in the exponential form. However, we know that experimentally this is not true. So what is unrealistic about the Einstein model is that it assumes the atoms vibrate with the same frequency and the atoms are independent from each other. So here we have an improved model that's called the Debye model. This is an attempt to include vibrational modes with different frequencies. So in this model, we're going to treat the solid as an elastic continuum. So the vibrational modes that are elastic waves will be traveling with the same velocity, omega divided by k, the phase velocity. And that means we're considering only the acoustic branch in the low k limit. So we're talking about sound waves, really. So the atoms do not have the same frequency, but they have the same amplitude. That's what we're assuming. And in order to find CV, we have to consider the density of states. The density of states, d of E dE, is the number of vibrational states with angular frequency between omega and d omega, or energy between E plus E and E plus dE. So we're going to find the number of states with k values in the range k to k plus dk. So what do we know about k values? Remember, we have used periodic boundary conditions for our traveling wave solutions. And for the k values, we have found 2 pi times an integer divided by capital NA for x, y, and z components. So we can see that nx times a is the length, and y times a is the width, and z times a is the height of the specimen. So these k values will change in units of 2 pi over lx, 2 pi over ly, and 2 pi over lz, because nx, ny, and nz were integers. So we have delta kx times delta ky times delta kz. So there is one k value in the volume 2 pi cubed divided by lx, ly, lz, which is the volume of the specimen. So 2 pi cubed over v volume in the k space will contain only one state. So you can see here in k space we have kx, ky, kz, and we have discrete values for kx, ky, and kz, and here is the volume delta kx, delta ky, delta kz that gives us one possible combination of kx, ky, kz and one possible state. So if this volume contains one state, the number of states per volume in k space would be 1 over 2 pi cube over v. So suppose that all possible modes are included in a sphere of radius k centered at the origin. So how many modes we would have in a volume element 4 pi k squared dk? So we're considering the sphere centered around the origin, and we are looking at a volume element. So if we look at a region here, we have the surface area 4 pi k squared, so this has a thickness dk, and we have the surface area 4 pi k squared, so this would be 4 pi k square. So 4 pi k squared dk would give us a volume element in k space. So 4 pi k squared dk times the number of states per volume, 1 over 2 pi cube over v, would give us the total number of states, v divided by uh, 2 pi cube. So instead of this volume element, if I consider the full volume of the sphere, 4/3 pi k cube, I get the total number of states, v over 6 pi square, omega cube over v cubes, recognizing that omega is equal to v times k in this continuum approximation. So the density of states, the change in the number of states with respect to frequency is the derivative of this, v omega cube becomes 3 v omega square. 3 and 6 cancel, it gives us a 2. So v omega square divided by 2 pi square v cube. V is the propagation speed of our elastic wave. So there are 3 different modes associated with each k, because we have 3 polarizations, 2 transverse and 1 longitudinal polarization, and omega may be different for each polarization. So we have the density of states, d of omega, it has to be considering 3 independent polarizations. So we have 3v omega square divided by 2 pi square v cube for the density of states. Now, Debye also considers the same quantum mechanical oscillators as Einstein. So here's our Planck distribution for average value of the occupancy, phonon occupancy number. H bar omega divided by e to the h bar omega over kt minus 1 is the average energy per quantum mechanical oscillator. So instead of getting the total energy by multiplying with 3 and assuming all oscillators are independent, we add up the contribution from different modes with different frequencies. So we will have the total energy, average energy per oscillator, density of states, d of omega, d omega. So now we have to determine the limits of the integration. If I integrate density of states from 0 to the so-called omega Debye, I should obtain the total number of modes. And what is the maximum number of modes I can obtain for 3n oscillators? Saying that each oscillator has a different mode, I would have 3n total number of degrees of freedom, giving me total number of possible modes. So now the propagation speed of the wave I can basically say is the sound velocity. So 0 to omega Debye. Now for the density of states I substitute 3v omega square over 2 pi square speed of sound cube d omega. So this integral 3v over 2 pi square vs cube is out of the integral. This integral of omega square d omega gives me 1/3 omega Debye cube. So that must be equal to the total number of degrees of freedom 3n. So omega Debye is found to be 6 pi square capital N over v to the power 1/3 times the speed of sound. That's called the Debye cutoff frequency. So the corresponding to Debye cutoff frequency is a Debye cutoff k value, so Vs times k Debye. So k Debye is then 6 pi square n over volume to the power 1/3. So to calculate the total energy, 0 to Debye cutoff frequency, all possible modes are included now. Average energy, Planck distribution multiplied with h bar omega, 3v over 2 pi square omega square speed of sound cube d omega. So 3v over 2 pi square speed of sound cube is outside the integral. 0 to omega Debye, h bar omega divided by e to the h bar omega over kt minus 1 omega square d omega, because the density of states is proportional to omega square. So this is going to give me 3v h bar 2 pi square vs cube 0 to omega Debye. Because I have h bar omega and omega square, that gives me omega cube d omega e to the h bar omega over kt minus 1. To get the heat capacity at constant volume, I have to take the derivative of this with respect to temperature. That gives me 3v h bar over 2 pi square speed of sound cube, 0 to omega dBi, omega cube, and the temperature derivative of 1 over e to the h bar omega over kt minus 1. And that derivative will basically give me e to the h bar omega over kt. The derivative of the top, that's minus h bar omega over kt square, and then the derivative of the bottom, e to the h bar omega over kt minus 1 square d omega. So and notice that I should get a minus sign because the derivative of 1 is 0, 0 times e to the h bar omega over kt minus 1 minus the derivative of the bottom. So the two minus signs will cancel and I will obtain h bar omega over kt squared d omega. So I call h bar omega over kt x. So h bar d omega over kt is dx, and I call x dBi h bar omega dBi over kt. So Cv becomes 3v h bar, because I obtained an h bar omega inside, h bar square divided by 2 pi square vs cube kt square, 0 to x dBi for kt over h bar is omega divided by x. So for h bar omega over kt squared, I have here h bar over I'm going to obtain basically kt over h bar to the fourth power. So let's see, for omega I substitute x times kt over h bar, so that gives me to the third power, and there's another omega here that gives me another kt over h bar to the fourth power, and from the d omega I also obtain kt over h bar. So there's 5 of them. So this gives me kt over h bar to the power 5, 0 to x dBi integral x to the 4 e to the x divided by e to the x minus 1 square dx. I multiply the top and bottom with 3n, and then I recall that omega dBi cube is equal to 6 pi square n over vs cube, and I define h bar omega dBi over k as dBi temperature, so that x value, x dBi, becomes theta dBi over t. So with that, I obtain 9n v k to the 4 t cube divided by 6 pi square n vs cube h bar cube, and 0 to x dBi x to the 4 e to the x divided by e to the x minus 1 square dx. And for the temperature, I substitute x. So x dBi is basically theta dBi over t. I substitute that in the limit here, and here I have also h bar omega dBi over k is the dBi temperature. So I substitute that here. So I obtain t over theta dBi cube. So theta dBi cube I can see is h bar cube over k cube t cube, 6 pi square n vs cube over v. So with that I can substitute it here. So this becomes basically proportional to t cube with this integral. It's a definite integral, so it's just going to give us a number. So if you look at the behavior of the this answer, so this is our final answer for the heat capacity from the Debye model. Now we're going to look at the high temperature limit. In the high temperature limit, h bar omega over kt will be small, so e to the x will be 1 plus x. So x to the 4, e to the x, x to the 4, 1 plus x divided by 1 plus x minus 1 squared, I obtain x squared. x to the 4 plus x to the 5 over x squared becomes x squared plus x cubed. If x is small, x cubed is negligible, so this becomes 0 to theta Debye over t x squared dx, which is x cubed over 3, which is 1 over 3 theta Debye over t cubed. So if you substitute that here, we have 9 nkt over theta Debye cube multiplied by 1 over 3 theta Debye over t cube gives us 3 nk, which is the Dulong Petit law, or for n equals n8 it becomes 3r, the molar specific heat. In the low temperature limit for h bar omega over kt, I'm obtaining infinites from 0 to infinite x to the 4 e to the x dx divided by e to the x minus 1 squared. This is going to give us a number, so it's a constant. So we find that the temperature dependence is only in the t over theta Debye cube, so it's going to be a constant multiplied by t cube. So this gives the expected t cube dependence of the molar specific heat. So let's summarize what we did here. So in the Einstein model, we considered quantization of harmonic oscillator energy, but we thought that all the atoms are vibrating in the same mode, the same angular frequency omega. Now, Debye takes into account vibrational modes with different frequencies in the continuum limit. So when we have the acoustic branch in the low K limit, and the modes are propagating with the same speed v equals omega over k, because remember that in that limit we had this linear relationship. So we have a, slope here, a constant value for the propagation speed. So if you go back to our omega versus k plot, so let's find our omega versus k plot. You can see here in the low k limit we have a constant speed, right? So there is this constant propagation speed. So that is basically the sound waves. So we're considering the sound wave propagation. So we have the same propagation speed for all these modes in the acoustic branch. The atoms are not vibrating in the same frequency, but they have the same amplitude. So in order to find CV, we considered the density of states, the number of vibrational states with angular frequency between omega and omega plus d omega. We have found that by looking at the possible k values we can have in k space, and by considering three different polarizations per mode, we have obtained 3v omega square over 2 pi square v cube for the density of states. And for the average energy, we use the same relationship that Einstein used, that's Planck's distribution times h bar omega, but we don't just multiply it by 3n to get the total energy. We consider that the fact that we can have different modes, so density of states multiplied by d omega. So if we look at the integral from 0 to the maximum omega we can have, density of states d omega, this gives us the total number of modes we can have, that is 3n, because we have 3n oscillators. So the propagation speed we have, omega over k, the constant propagation speed, is the sound velocity in this medium. And we can obtain the Debye cutoff frequency by considering this integral from 0 to omega Debye, d of omega d omega is equal to 3n, the total number of oscillators. Now, we can also obtain the corresponding maximum k value that we can have in this limit, and by looking at the integral from 0 to omega Debye, average energy per oscillator, density of states d omega, we obtain the total energy, and by doing some math we have obtained t over theta Debye cube, where theta Debye is h bar omega Debye over k, times the integral 0 to theta Debye over t, x to the 4 e to the x dx divided by e to the x minus 1 square, where x we have defined as h bar omega over kT. So we looked at the high temperature limit, so we looked at the right hand side, the integral basically turns into 1 over 3 theta Debye over T cube, so that gives us 3 nk or 3 R for molar specific heat, the Dulong Petit law. High temperature behavior in the classical limit is recovered. In the low temperature limit, the integral limits are changing from 0 to infinity, so that makes it a constant, so we don't have to evaluate this integral. We find that the temperature dependence is just given as T cube.